as we building this tree, we define the threshold for splitting. Actually, this threshold for splitting, it's like you do the threshold for splitting when you sort along particular axis. So you also have to, maybe this one, this is 2, sort along feature dimension. And then you set up the thresholding, and that threshold value, let's say x0 equal to 1 or x0 equal to 15, these value depends on your training samples, right? Because that is like, if your training sample are so mixed together, of course, at some point you may not be able to find a thresholding value along that axis, so you have to go to another axis to find the thresholding value that you can separate the data into 2 classes. Another thing that we have to be careful about is the fact that how many times you can split at one decision. Let's say in this decision, I only do binary splitting, but you can do triple or 4 splittings or 5 splittings at once. That is something that you probably have to do some kind of validation to find out, like which number of splitting is the best. But probably the easiest to understand is the binary splitting, because you only say one left, one right. If one of them have like a mixture of nodes, mixture of samples, so the node is not pure, then you have to go further and make decision. Another thing that you should keep in mind is that one of your child nodes, either left or right, they could be leaf nodes for both of them. They could be one leaf, one decision, and they both could also be decision nodes. If both of them are decision nodes, for example, if this one is not a leaf node but actually turn out to be a decision node, what this algorithm do is that they probably have to sort out all the childs related to this node up until the end, and after that it will go up here and try to sort for all the child in another node. So that is what's going to happen if it turns out that 2 of your nodes are both decision nodes. Usually this happens when you sort out all the feature axes and you cannot really come up with like a pure set of nodes at all. But this is like a very special case. Of course, this will not be in your exam. Your exam would be something like simple as you can always find a set of nodes. You will always be able to find the samples that are pure, they belong to the same class, and then you can assign it as a leaf node, and the other one may be another leaf, or it could be another decision node. So yeah, that's what's gonna happen in our course. We won't go as far as try to ask you to write a code for something too difficult. Yeah. So what this does is that you can see that this is like a way of making like the algorithm for forecasting based on the majority vote of the, let's say, some local area that is somewhat optimized with your data samples to be as homogeneous as possible. For example, when you find, let's say, the node that is totally pure and you set a thresholding, that threshold defines that, okay, with this area, this is the maximum threshold or maybe minimum threshold or maybe the best threshold that I can go, that gives you the node with the samples that are pure as possible. So actually, if you write this mathematically, it becomes some kind of optimization problems that look like this. Where, let's say if this one is like a prediction or maybe the majority of that samples, maybe majority vote of the class of that particular samples, like all the red, Most of them are red, most of them are green. It's like a representation vector of that sub-region. And then what you are optimizing that is the data sample. Yj here is all the data sample within that region. So you can think of when we do the partitioning, right? And we say that, oh, they're all pure. That means that first thing that you get is like, what is the majority of this group? And are all of them aligned with your majority? So that will be minimized. And the thing is, what you are optimizing was actually the area, like how far you want this area to cover. Is it just this group, or is it just bigger, or is it smaller? So whether or not it's bigger or smaller depends on how much your region can cover. So yes, that is why we set up this to be like a majority vote of that region. And this one is like all the samples in that particular region. And what you're minimizing is actually you're minimizing the region R1, R2 up until R3, but I haven't wrote it here. Because the thing is, you don't normally know how many regions you will actually end up with. Just like the example that I showed to you previously. It is like if my data sample are just slightly different from what it used to be, let's say if I happen to have one green dot here, then your nodes will be different. That is, when you start first partition this, you will have like one pure, one mixed, right? When you start partition, you have this one, okay, one pure, one mixed, one mixed. You may still stubborn enough to go further, then you have one pure, one pure. You can go that way as well. It is like there is no defined goal for how many regions you would end up with. It depends on how can you split them. Can you still splitting them, or you cannot split them anymore? So that number of region here, that R1 up until RT here is still varying. So you don't know even how many T or how many regions are unknown as well. Thing is, if you think about this optimization problem, it's actually highly nonlinear, highly discontinuous, because we're talking about region partitioning. Actually solving this problem directly is infeasible. But you've seen how I partitioned it before. So actually what I just showed to you previously was like a greedy algorithm that we adopt to solve that problem that you've just seen. Yeah. So actually I wrote somewhere around here. Actually I'll skip that one. Here. Unfortunately, both equation 1 and equation 2 is computationally inefficient to solve. Like you can't really solve them. So we actually use some kind of top-down greedy approach that we just showed to you, that you make a recursive decision of decision node, leaf nodes, pure nodes, whatever, to solve this problem. So it's kind of solvable, but whatever you get from this greedy approach is actually good enough at this moment. Yeah. And here I wrote equation 1 and equation 2. This is equation 1 you already see. Actually, equation 2 is slightly different, but what you're maximizing is like the majority, sorry, not majority, the probability of all sample being to that class. And minus with 1 is like the maximum of the probability value is 1 anyway. Yeah. So it is like you change from this square root, sorry, not square root, like the square norm, to this one minus. That is, if you want to change from maybe this loss, actually this loss is suitable for regression task. And this one is more suitable for classification task. Actually, for this loss, there are two alternatives to use it. You can use Gini index or entropy value. I'm not sure about Gini index, but usually people say Gini index is something that they use to approximate, or maybe to kind of like, because if you compute the entropy directly, sometimes it's too complicated, as in there are logs term here. Some people, they don't like it. Some application, when you have the logarithm term, it may result in some kind of underfloating or be overfloating. But anyway, with the entropy, I can describe why this one matched the one above here. Let's say if you have a probability of 1 or 0, this entropy value will have the value of 0. Okay, maybe I'll just put this way. P-value, that is a probability value. So this is 0 is here. If it's 0.5, it will have some high, not high, it's like this entire, if the value here is like, floating value in between, okay, 0 and 1 will have this value. If the value is in between here, it's like it's going to be some minus with some number that is non-zero. And when you multiply that minus sign with another minus sign, then it will be like non-zero. But actually, if you can plot a graph, it will look like this. And the maximum usually being when your P is 1/2. So your entropy will be maximized when, like the probability of belong to that class is kind of uncertain. But the thing is, what you want is you want it to be really certain. You want it to be like either 1 or 0, like all or nothing at all. So that is the reason why you can use this entire loss to substitute the one above. This is just a rough idea of what they are. Actually, for these two quantities, it's better to kind of get that insight from something like information theory, which I'm not able to got into here. But actually, I can say that actually what is equivalent between this one down here and that one down here is the fact that this negate of log is actually represented by 1 minus P for the Gini index. That is more like how Gini index is varying with the entropy. But actually, there are some kind of proof to show that Gini index is kind of like measuring the total variance of sample belonging to that class. Anyway, that's it. Actually, we already know how we build a tree. So that's how we solve for the region minimization problem. Like region error, minimizing over regions. So minimizing the loss, the error over some kind of regions partitioning. So that is like your core idea. And you already see how it's done. But the thing is, what I haven't done is that I already mentioned that if you find a pure node, you can use the majority vote to derive your conclusion, right? Actually, this is like for your leaf node if you are doing classification. But if you are doing regression, what you would do is that you just compute the average of the target value of your training samples belonging to that region. So that becomes your y-hat. Actually, what I would say is that originally when people come up with this idea of decision tree, as you can see, decision tree is very much simplified. As in, majority vote still kind of work, but this one should not work. Because if you compute the average value of the target value in your training samples, but you are having your testing sample, and perhaps your setting environment is too different. As in your testing environment, maybe you have different types of noise versus your training. That means this value should not be really good, right? If you just infer your result based on the training value purely without using any information from your input. So that is why in the beginning, the decision tree was performing very bad, especially when you compare to like regression task, the linear regression or some nonlinear regression. But in fact, the decision tree becomes much better when you include some additional techniques that we will learn today, like backing, random forest, bootstrapping. Actually, those stuff will turn this generic algorithm into something that nearly able to compete neural network. And actually, it can compete neural network when your data samples are really small. Yeah, actually better than SVM, especially for GX Boost. So that is pretty much it. Just a little side notes. When you use, let's say, tree-based algorithm, there are a few things that you have to keep in mind that they could be your hyperparameters. That is the dimension, or maybe what we call the tree width. What are they, right? Actually, if you remember last time that I draw, okay, not there yet. Okay, maybe this decision tree that I draw. The tree width is like the number of hop that you got from here to here, given that they are maximum. Or maybe, like you will know it maximum if you start from the first root, right, to the last leaf. That is your tree width in this case. It's defined as the maximum distance. And what you have to keep in mind is that unlike many algorithms that you learned before, like support vector machine, regressions, those guys will have the weights, like a linear combination weights as their parameters that they learn when do the training. But in this case, for tree-based method, what is the actual parameters is your splitting threshold. Like how did you split when you classifying the class? So actually there are these values. So when you do the training, you will collect this thresholding value as your parameter. What next? I think that's pretty much all. Yep, this is like an example that if I kind of follow my original example, it would look like this. And this is pretty much what I just described. So actually, building a tree can be implemented as a recursive algorithm. What does it mean is that when you first have your decision node, right, you then start to find the splitting, and you find the splitting thresholding, then you can define its two children, right? And you start to identify whether or not that children is like a leaf or another decision tree. And once you get that, okay, maybe this one is leaf, this one is decision tree. Then for this decision tree, this one is decision node. Once you know it's decision node, then you now know that you have to do the same thing. So every time the algorithm would run as if it's kind of like recomputing the same procedure again and again, just like this red rectangular that I draw here. Like the first time it's just this one. The second time when it's are able to find the decision tree, just do another one. Next time is another one. But then when you reach to the point where you are not be able to split it further, let's say two of your children nodes are leaf nodes, then you're done. So what you have to do as you do the implementation, which will be like something that I would ask you to analyze, as in in the lab session, I already provide a code that you can run. Like you don't need to do anything with the code, but you have to come up with the flow chart of how the tree building method work. You have to actually go into the code and see, but I will give like a brief of the lab next week. Okay, so you can look at this. You're already familiar with the procedure. So yes, first is assign the current nodes as a root node. Second, ask yourself if you can split the data. If yes, first you come up with the current node as a decision node, which you already split your data. Like you already know that it has two splitting. One is left, one is right. Then you start to look at your child. Can your child be further split? If no, then it's a leaf node. If yes, then it's a new decision node. Then all you did was that then you start to assign the child for this decision node and go back to that procedure again as if you don't care what's going on up here, but then you got here and then you start to be like, okay, then does this decision node has the child? Can it be split? Yes, no, yeah, and go on, so on and so forth. So as a process of building this tree, you have to collect who is the child of that node that you are looking at. And if they don't have a child, like they are leaf, then you just assign the value that you would give as a prediction, because it uses the majority rows of the target value in your training anyway. It is like as a process of your tree learning, you can already assign this value. Like you don't need to recompute it again. So all you did is like when you use this model in real time, you only get if your data sample fall into each case. And if it falls into like each particular case, you can then return the value of that target value. It could be either the majority for classification. It can also be the regression if you're working on regression tasks. If it's regression, then it's just the average value of your target in training. So it's simple as that. Yeah. Let's have like a 5 minutes break.